That you guys have regarding problem set 2. I'll briefly just go over what is expected from questions 1 and 2, and Pranjal will talk about 3. It's actually very simple. You don't have to do anything very complicated. For the first question, you have seen Euler's method and you have seen modifications to that as well. You just have to test out any small new change that you can make to any of the existing methods. A lot of people have submitted 3 existing methods for this. I mean, that's also acceptable, but what we wanted was something new from your end. And it doesn't have to be better than Euler's method, or it doesn't have to be better in any sense. It just has to be different. And yeah, we've made the error analysis part for that optional.
Aditi, can you share your screen as well? We can show them the problem set.
Yeah, okay, sure. Is the problem set visible?
Yes, it is.
Yeah, okay. Yeah, so question 1, a description, error analysis is optional, and a few points regarding anything new about your method, good or bad, doesn't matter, just 1 or 2 points about that. For problem set 2, a spline basically refers to some kind of a polynomial. Simpsons also does that for your parabolas, but you can explore beyond that. And the hint is given. I mean, you can use Taylor series to just work this out. And there's one question that we discussed in the first part of the second session. There's a hint. There's a very big hint over there also, in case you didn't notice. And yeah, for this we need to see code. So submit your code. It would be nice if you so that we can see it, and it would be nice if you can submit one test case also, like it's given over here. You check the integral on this and then submit it. Yeah, so that's it from my side, Pranjal.
Yeah, so problem 3 is basically a very similar numerical to the example we discussed in class, except like when you get an expression for u x comma t plus delta t, it will involve expressions of u at time t and at time t minus delta t as well. So basically you need 2 initial conditions, right? Because using 2 rows, you'll get all these successive rows. And in the example discussed in the session, the RHS had only u values at t. So you just needed 1 initial row. Here you need 2 initial conditions. I've already given you 1 initial condition in the problem that at time t is equal to 0, u depends on x as 2x 1 minus x. Try to get another initial condition from the dou u by dou t is equal to 0 expression, and just use central difference approximation in that. So this is, I gave you a very big hint now, like using both these, like using both the 2 equations you get, you can find all the successive rows. So that's basically how you do it. I hope that's clear. In case you have any doubts, you can answer them. Yeah, so Kushal Mehta, can you tell like where exactly are you facing an issue? What are you planning to understand?
Pranjal, I think we can go over the last question once again.
Okay, fine.
Share your screen as well.
What?
Can you share your screen as well if you have the assignment with you?
Yes. Is it visible?
Yeah, it is.
Okay. So basically, I've been given one expression, right? Dou square u by dou t square is equals to c square dou square u by dou x square. So we'll be using like central difference approximation for that. I've given you a hint for it as well. So you'll be using a central difference approximation for that, and you'll get an equation. And on the LHS of the equation, basically you want to find the value of u at x comma t plus delta t, right? So the equation for that will contain on the RHS, it will contain the terms of u, I mean the values of u at x comma t and x comma t minus delta t. So for that, you basically require two rows. And using those two rows, you'll find all the successive rows. By two rows, I mean if you make a stencil, if you replace u x comma t with u I comma j, where I is index of position and j is index of time. So basically, you need two initial rows. J is goes to 0 and j is goes to 1. Those two rows you need. And using those two conditions, you can find all other rows, like the example we discussed in this session. So for finding the values of u at j is equal to 0 row, I've already given you the equation, like the initial condition, that is u x comma 0 is 2x 1 minus x. And to find another initial condition that you can use, I've given you another hint to use dou u by dou t is equals to 0, t is equals to 0, right? The initial velocity will be 0, right? Because I'm just leaving the string like that. So use the use central difference approximation for that as well. So you'll have two conditions, like two initial conditions. You can use both of them to find all the successive rows. And the code for it is very similar to the one discussed in class. Are there any other doubts?
You guys can free to ask any doubts that you want. We really want that you guys learn something out of the sessions, and you should be able to solve the assignment on your own. So like if you guys have any doubts at all, feel free to ask us. We'll be there to guide you.
And if you submitted assignment 1, then you should definitely not leave this halfway, because you've already done a lot of hard work. It shouldn't go to waste. So it's better that you try and try to finish this also. It's really not that hard.
Yeah. And once again, we'd like to say that this assignment is a relatively difficult one. If it's hard for you, then it's probably hard for everyone else as well. So put in your best efforts, submit whatever you can. Just don't sit out of the competition just because you feel that you have not done a good enough work. So we will be lenient while correcting your work. So just please give your best and submit whatever you can.
Hello, am I audible and visible?
Yeah.
Okay, wait, let me share my screen. So is my screen also visible now?
Yes, it is.
Okay, guys, before we start, since today is the last session, I thought I'll introduce you guys to a few things that Mathematical Club does to help keep you guys engaged. So number one, we have an Instagram page. So on this page, we regularly talk about all the events we're conducting and also have a few questions on our stories and posts and other things like that. So if you ever want to keep in touch with mathematics and you want to be updated about our events, this is the place to follow. I'll copy this link and actually put it in the chat so you can go ahead and start following right now. And apart from that, we also have a LinkedIn. So for those of you who are trying to build a professional network with people who are part of the mathematics club, or just want to stay updated with what more the math in today's world is like, then you can follow us on LinkedIn, to which also I'll send the link right now. So you can go ahead and do that. And lastly, this is our website. I think a lot of you might have seen this website before, because we have our summer school sessions uploaded here. But more importantly, we have something called the mathematics competition coming up. We are calling it the Srinivasa Ramanujan Mathematics Competition. So some of you might be aware of competitions like Putnam in the US. So we are trying to create an intercollegiate competition just like that. It will be mostly high school and college mathematics. So it should be doable by most of you attending this session. And there will be 2 rounds. The first round will be an entirely online round. It's just a qualifier round. So no matter where you are from, we encourage you that you attend that particular round. The second round will be attended by people who performed really well on the first round, and the second round will be a subjective round, and that will be held offline at IIT Madras. So if you want to, the registrations will open from July 1. So for now, if you want to stay updated, there is the link for the WhatsApp group on the website, and we strongly encourage you go join that group also. Let me share the link for the website too. And lastly, but not the least, some of you might be attending these sessions from the YouTube channel also. But regardless, let me share the YouTube channel with you. Here we'll have a few videos. Obviously, we have the recordings of the summer school that we put here. And apart from that, we also have a few questions and interesting stuff that we put here. For example, this is one video where we talk about how we can represent complex geometric series visually and things like that. The aim of the YouTube channel is to keep you guys engaged with intuitive content. So regarding that also, I shall attach a link right now. So we strongly suggest that you guys follow these channels if you're interested in mathematics. So yeah, that's about it. Do you have any questions? Okay, I assume there are no questions, so I leave it over to the coordinators to start the session.
So hi, just before we start, we just want to give a shout out to all these guys. They have successfully submitted assignment 2 quite quickly. So Ishan, Sonalika, Praveen, Ramata, Amrit, Ritvik, Vishwesh, Manas, Harit, Shuvam, Jasmeet, Shashi, Nitish, and Shiv Prasad. Congrats. I'll start in like a minute or two. We're having a little bit of a technical issue. Okay, so I'll start. So my name is Achintya, and the topic I'm going to discuss today is linear constant coefficient differential equations. That heading itself seems kind of intimidating. So let's break it down. So linear constant coefficient. So we'll start with the linear part. So linear differential equation. Basically, these are differential equations where any derivative, let's say dy by dx, any derivative term, or even just the normal single term, these don't have any function associated with them. Like they're not squared, or it's not like sine of this. They're basically independent. And constant coefficient, well, the term is explanatory. Constant coefficient is just, every derivative term has a coefficient, let's say a, and this is not a function of y or x. It's just independent. So that's what linear constant coefficient means. So in general, the nth order linear constant coefficient differential equation is of this form. The way I'm going to represent it throughout this session is going to be summation ak dky by dx, a ranging from 0 to is equal to f of x. This is how I'm going to represent it throughout the session. Sometimes you'll see me using a different notation where it goes from where I replace y with x and x with t. This is the same thing. It's just a different way of writing it. This comes up in physics a lot. So I use this sometimes. But keep in mind, these two are the same thing. So an example I'm sure all of you would have seen is the spin system. The governing differential equation is d2x by d2 equal to minus omega square x. And this is an equation, I mean, you would have seen in 11th and 12th or whatever, first PU, second PU. And this is a very simple differential equation. We are going to deal with the general. So quickly type in chat what is the solution to this. I haven't given options because by giving the options, I mean, it becomes quite obvious. So just quickly type in chat what this is. In DeepStat, Aditya, you're right. Can you simplify this? Can you write this in terms of in another form at least? I want y equal to something. Yes, okay. Samant, you're right. Others are not. Yeah, Sonalika was there. So I mean, you can solve this. So dy by dx is equal to ky. Simplifying. Right. One second. So 1 by k integrating 1 by k ln y equal to x plus c. Remember, the c comes here. People added the c at the end. The c should come here. So the actual equation is, so if you write in exponentiate both sides, you get y equal to a e power x, where a is the constant. Because when you exponentiate both sides, you can see it becomes a multiplicative constant. So yeah, move on with the check. Okay, give me 1 second. So that is a solution. Yeah, that is a solution. So what about the solution to this? Oh, thank you. Thank you. Yeah, what about the solution to this? Come on, you guys should have seen this. This is the solution to this. Type in chat. Yeah, I fixed it. Okay, you're right. Okay, so the solution to this is, I mean, I've written the solution here, but yeah, this is the solution I've written here. However, the solution you would have seen is a sine omega x plus b cos omega x, or omega t in this case. So this is the solution you guys would have seen.
Achintya, I think your
Yeah.
screen is frozen. We are still seeing your notepad at y equals a power x. Yeah.
Better now? You see?
Yeah.
Okay.
It's
Yeah, sorry
okay.
about that. Yeah. Okay. So yeah, this was the question. Sorry if you guys didn't see that. So yeah, this was the question for spring. What is the solution? And the solution I've written here is in terms of exponential. However, the solution you guys would have seen is more of this form. And I'm just going to show you these two are the same. So you know sine can be represented in terms of exponential. This is e power I omega t minus e power minus I omega t by 2i plus p by e power I omega t plus e power minus I omega t by 2. So simplifying this, we get it's a by 2i plus b by 2 times e power I omega t plus a by 2i minus e by 2 e power minus I omega. So we can represent this as some alpha, this as some beta, and we get a solution which is shown here. It's the same. So what do you guys notice which is similar in both of these solutions? What is the similar defined property? Second chat. Yeah, e power I omega. Is it always e power I omega t? Yeah, that's true. This term is also a solution. Yeah, that's the next step. We'll come to that. Yeah, correct. Exponential solution. So something seems to be interesting about the exponential function. And well, what is the exponential function? Should block this today. The interesting thing to note here is in e power s, x may be complex. So in general, it's actually so exponential solution of e power s has two forms. So s is equal to a plus I omega. So actually is of the form e power a, e power I omega. Right. So yeah, there are actually two terms here hidden inside this one function. And this is actually important because sometimes the solution is complex, sometimes it's trivial, sometimes it's the combination of both. So why is it so special? And interesting to note. Okay, first of all, let's have you guys guess. Why is it so special? Why does e power sx appear in differential solution? Differential equation solution. Who answered this? Yeah, shout out to Vasudev. You are absolutely right. So yeah, if you differentiate e power sx with respect to itself, you just get s e power sx. Yeah, it's differential. It's just itself scaled, and this is a very interesting property. This is why it comes up everywhere. Yeah, take it. Yeah, this particular thing has a name. Some of my IIT friends will know it, but yeah, so basically e power sx is an eigenfunction of the derivative operator. These are just fancy words. This literally means what this equation says. So an eigenfunction of an operator is a function which, if you pass through the operator, just gets scaled. And that's basically what this is. You don't need to know this. This is the point I mentioned. So yeah, now that we know this function is kind of interesting, let's see what happens if we try to analyze it as a solution. So we want solutions to differential equations. I mean, that's why we started. So if you have a general differential equation, dy is equal to f of x. Let's take a particular case where this is equal to 0. And let's see what happens if we substitute e power sx as a solution. We get k equal to 1 to n, k sx by dxk equal to 0. And notice the number of times you differentiate this. Like if we differentiate it once, we get s e power sx. Differentiate it twice, we get s square e power sx, because s is just a constant. Derivative of s with respect to x is just 0. So similarly, so this thing simplifies very nicely to ak s power k e power sx is equal to 0. And e power sx is independent of k, so we can take it out. So take it out here. Just e power sx. And e power sx is never 0. Because the real part is never 0, imaginary part is never 0. So we can just cancel this because it's 0 on the other side. And so we get this thing is equal to 0. And if you write this out, this is at an s power n plus an minus 1 s power n minus 1 up till a1s plus a naught is equal to 0. Now notice this is just a polynomial. And okay, I don't know if you guys know this, but a polynomial of degree n always has n roots. Assuming the roots are complex, of course. So the roots also may be complex, but it always has n roots. This is a guaranteed thing. So some may be repeating, but that's always. So now we know that. So we know. So let the n roots be like s1, s2, sn. So remember, what are we solving for? So we were solving for e power sx. We were trying to find the function e power sx as that it is a solution to this differential equation. So now we know that e power s1x is a solution. E power s2x is also a solution. After e power snx, these are all solutions. So notice now we have found n solutions. Can you think of any other solutions? Can you somehow make solutions with this? Answer in chat. Is there any way we can make solutions? Yeah, right. Linear combinations of them are also solutions. So I will leave this to you guys to verify, but the general solution can be written like this. Okay, that's not easy. A1. Yeah. This is the general solution. Notice these are all special cases of this solution. Now, you guys, I leave it to you guys to prove that this solution is in fact a solution to the differential equation. It's not hard. Just substitute into the differential equation and you try simplifying, you'll see it comes out naturally. Yes. So yeah, I've just written it out here. Notice the other combinations are also solutions. So now let's try solving something. So this is the dampened spring oscillator. This is the differential equation for it. So let's try solving it. So what would be the method to solve it? So I just look at that. The differential equation is due to x plus 2 gamma x by dt omega square x is equal to 0. So what should I do here? How should I solve this? We just looked at a way to solve stuff. How should I solve this? Yeah, correct. So assume, so let's say e power sx is a solution, and let's substitute it. We get s square e power sx. Oh, sorry, my bad. We get d2 e power sx by dt2 plus 2 gamma d e power sx by dt plus omega square e power sx 0. So this is just s square e power sx plus 2 gamma s e power sx plus omega square e power sx equal to 0. Can cancel e power sx. And we get s square plus 2 gamma plus omega square equal to 0. Solutions to this. This is a normal quadratic equation. Solutions are minus gamma plus minus root of gamma square minus omega square. Yeah. So yeah, you guys can verify. This is just a normal formula, minus b plus minus. Yeah. So some of you would have seen this actually already. This is the dampened oscillator. So the general solution is of the form a e power s gamma plus root of gamma square minus omega square t plus d e power minus gamma minus root of gamma square minus omega square. Remember, it's a linear. Final solution is a linear combination of e power the root. So, yeah, the final solution. So I've written it. Yeah, it looks a little different. It's the same. So now we know a solution for the homogeneous equation. What about a non-homogeneous equation? This is called homogeneous, by the way, where the driving force is 0. So here the driving force is not 0. So that's what we are actually trying to solve, because this is what will come up most of the time in the real world. We'll have some input function and we'll get an output function. So this is what we actually want to solve. And it's, yeah, it is not very simple, but we are going to analyze a very special case. The forces of the form e power sx. Okay. Yeah, we are going to analyze a very special case of this differential equation, where we have dk, dk, dxk, k ranging from k ranging from 1 to n is equal to e power sx. This is a very, very special case. Not necessarily any force will help, but yeah, we're going to only analyze this. So let's say s naught x. Okay. So can you guys quickly give me a solution? I'm not asking the complete solution. Just give me a solution, one solution. Find solution considering it as homogeneous. Yeah, right. Okay. Then yeah, you are actually right. Homogeneous solution. Yes. I'm not going to review the homogeneous solution right now. I'm going to assume system is at rest in the beginning. I'm going to review only the particular solution. For those of you who know what that means, it's okay if you don't. So what is the particular solution? Whatever. Okay, so a good guess we can have is we can try substituting some scaled constant times e power s naught x. Remember the driving force is this. We can try substituting this because we can't just substitute e power s naught x because s naught is a given quantity. It's given. So we can't alter it. If you substitute it here, you will get some inequality. So if you scale it, we get some sort of changeable factor we can analyze. So a good guess is just to substitute this. And so we get k equal to 1 to k a times differentiating the k times s naught to k e power s naught x equal to e power s. So yeah, we can of course cancel this because it's independent of k. And so we get a is equal to 1 by summation k equal to 1 to n ak not power. Yeah, okay. So we have this. So what is the final solution? This scaling factor time. So this is the final solution. So, yeah, so now we have a method to solve it. Remember in the first case, we found S in the case where it was homogeneous. Here, S naught is given. So the constant is fixed. And so we can't scale this solution. So if I scale this by A, this won't be a solution. Because the scaling constant is fixed. And for those of you who know that there is actually another homogeneous solution here, I'm not dealing with it because I'm assuming the system is at rest to begin. It usually this solution decays. So I'm just going to assume it's at rest at that. So yeah. So for string oscillator, we can take our general string oscillator and we can try solving it. So the method remains the same, but instead we substitute e power I omega naught. And further solving it, I won't go through this because I've already done it for general. Yeah, further solving it, this is what you get as the constant. So now let's talk a little. I'm going to go a little bit off topic there and talk a little bit about linear independence because we need it for the further topic I'm going to discuss. So suppose you have this given equation. What can I say about ABCD? Chat wants put a poll. Will you please show force oscillator? Okay, guys, have a look at this. I'll do it after that. Just give me a second. Oh, it's multiple correct. Sorry, I didn't put it. Multiple correct. Although you can also submit it. I'll consider one. So it's interesting. So okay, while the poll goes on, I'll just someone asked me to explain forced oscillation. So yeah, forced oscillation. So yeah, basically the idea behind forced oscillation is you substitute. You are given some differential equation is equal to e power ft. The forcing term is this. So what you do is you assume the solution is of the same form, but you just scale it. You assume the solution is of this form, substitute, and you find it is in fact a solution, and you can find the value of A. The value of A is here. Sorry, here. I've written it down here. This is for general. In this particular slide, I have taken just a string oscillator, and here I substituted A for I omega naught t. And after solving that, you get the value of A. Is that clear, or do you want me to explain it again? Yeah. Okay. And yeah, most of you guys are right. So yeah, answer is here. Right. So actually the actual answer is D, but B is by extension also an answer. Because if A equal to C and B equal to D, then A plus B equal to C. So why is this true? Well, a hint you can think about is remembering vectors. So these kind of behave like vectors. So remember, if you had A I hat plus B j hat is equal to C I hat plus D j hat, then you would say A equal to C and B equal to B. This is kind of similar in the sense that e power ik1 omega t and e power ik2 omega t are what is called linearly independent. And that's just a fancy way of saying that A times this is not equal to this. You can't find in A such that this is true. This equation is true. You guys can see how this translates to this equation. I mean, that is, I leave it up to you. It's a little bit of a, but yeah, it does translate to that. So the important thing to note is this particular thing, because it's going to come in handy soon. Also, yeah, true. It will also be. Yeah, Harit, you're right. And actually, yeah, because the complex line and the real line are also linearly. They also behave like vectors. So, yeah, okay. So now we are going to look at a very special function. Remember, we had a look at e power sx. We said f of x is equal to e power x. Now, this is a very special case, right? What we wanted is a general case where this differential equation is equal to some f of x. Now, we wanted a way to solve this general thing. So let's make it a little bit more general, and let's look at a series varying from, okay, let's say bk e power ik omega. And I'm going to write k ranging from minus infinity to infinity. I'll explain this. So we're going to look at this thing. Now, it seems you have downgraded the exponential, but remember the complex exponential is of the form e power st, and that is of the form e power say some you know k plus e power I omega. But and we have only taken the complex part. And yes, that's true. It's kind of a downgrade, but you'll see this is actually turns out to be useful. And that's because I want to deal with periodic functions. Now notice this thing is periodic. This thing is not actually periodic. I mean, it may be periodic, but in general, it's not periodic. So why is this periodic? Because the complex exponential is in fact periodic. Here, e power ix. We know it's the same as e power I2 pi. Right. So yes, this is in fact periodic. B is independent of time. So we say we are looking at this is equal to f of x or f of t in this case. So if we have a differential equation of the form, okay, so we're doing t, right? Let's do t. X a is equal to summation bk e power I k omega naught t. This k from minus infinity to infinity. So yeah, I written k going from minus infinity to infinity. Some of you might think this might go to infinity or something, but no, that's not true. Because I can always, if I want the summation to range from, let's say, 1 to n, I can always define bk such that it's some value between 1 to n. And it's zero otherwise. So then it will just become a summation. So I'm writing this because it comes in handy later. But yeah. So how do we solve this? So again, the answer is to assume a solution. So can you guys guess what solution I might assume? Type in chat. You guys have a guess. But what is K? I mean, yeah, you're right, Moksha. But what is K here? K is running variable inside a summation. There should be some summation, right? Right, okay, sorry if this is confusing you. I'll change this variable. Let's say J or something. It's not the same K, obviously. So, any guesses? But if you have doubts, also ask the doubts. If you feel I'm going too fast or you didn't understand something, please ask. Okay, so a good, I mean, for the case where this is a single exponential, we would have guessed AE for I omega t. In this case, S equal to I omega. So here we just guess, instead of this single coefficient thing, they'll just guess the summation. So I better just guess the summation like CK e for IK. This is an absolute guess. I'm just going to randomly guess this. And we'll see where it goes. So I won't solve the general thing. I mean, may get a bit complicated. So I solve the special case. We'll again take it's not clear. Guys, other coordinators, can you verify? Is my voice clear? Okay. So I guess I should. All right. So we'll solve the second order differential equation, a dampened oscillator, and you can generalize it to an nth order differential equation. I would have to guess it's the same thing, the same method. So it shouldn't matter. It's equal to summation. Okay. So let's assume some x summation k equal to minus infinity to infinity ck. Remember, ck is not defined here yet. This is just some random variable constant I'm taking here. Yeah, you could solve the equation for each. Exactly. So yeah, we'll substitute this here. And if you differentiate, you get summation k going from. Listen, we can take the derivative inside the summation. Ck is not affected by the derivative, and only e power ik omega naught will be affected. So it becomes ik omega naught square e power ik omega naught t. Second derivative of exponential plus summation k going from minus infinity to infinity 2 gamma ck ik omega naught e power ik omega naught t plus summation k going from minus infinity to infinity omega square ik omega naught. These are different omegas equal to summation k going from minus infinity to infinity. Oh wait, okay. So dk e power ik omega naught. Wait, so this is wrong. So yeah. Thank God we have to. So basically, we started out with this, substituted x, and we got this as a solution. I mean, we didn't get this, we got this equation. So let's try simplifying it. So one thing to notice is ck is common. ck is common, and the exponential is also common. And we can take the single summation of it. So we get summation going from minus infinity to infinity ck e power iq omega naught t. And the remaining terms. So this term is just minus k square omega naught square plus 2 gamma I k omega naught plus omega square is equal to summation k going from bk e power I k omega naught t. Right. So now a trick comes in handy. Remember we looked at this thing. Remember this. If you have different exponential frequency like k1, if we have k1 and k2, then we can just equate the coefficients. Yeah, same thing happens here. So we can just equate the coefficients here. So we can say for all k, this is the for all symbol. Means for every single k I can find. So here minus infinity ck minus k square omega naught square plus 2 gamma I k omega naught plus omega square is equal to bp. This is true for all k. And remember what we wanted to find. We wanted to find ck because ck is part of the solution. So our solution for or at least ck is equal to bk by bk is a given quantity by omega square k square omega naught square plus 2 gamma I k omega. And yes, this is our final. So this is ck, and we know our solution is solution. This summation here is from minus infinity to infinity ck equal I k omega. And we know what ck is very big in terms of bk, and bk is a given quantity. Yeah, this is how we would solve it. You can see how this generalizes to our general differential equation. Same thing. Just assume the solution is some ck e power I k omega naught t. Substitute, solve. You will get the value of ck. Yeah, I am not going to solve this, but I'm just going to mention it. I leave it in the PPT. If you guys want to try to solve, you can do it. So this is just a normal LC circuit. You can apply Kirchhoff's equations and you will get this. And we'll just give you this because this is just some physics you may or may not know how to apply Kirchhoff's equations. Yeah, these are the equations you'll get, differential equations. You will have two variables, Q1 and Q. And so the way you would deal with this is to take Q1 equal to some Tk, Tk times e power I k omega naught t. So we take Q1 is equal to summation Tk e power I k omega naught t. And Q is equal to some summation vary from Tk e power I. And you'd solve for Ck and Tk. And this turns out this is the solution. I'm not going to do it. Okay, so it's at some time t. It's not at initial time. Q and it's not Q, it's Q. It's Q1. The different locations charge on capacitor 1 and 3. Yeah, so that's the basis. So now we look at this very special function. Right? Why this function? What is so special about it? So a hint is what is this function? So can you guys guess what is the special function? Why did I deal with it? I said I'll generalize it. This is not yet, doesn't seem general yet. So why did I take special summation function? This thing, this driving force. Why this? Yeah, it's a function. What? Why this function? What is the session name? Yeah. Yeah, you're right. Others, come on. No, so yeah, so this is Fourier. So this name of this thing actually is two words. The first word is Fourier. What is the second word? Yes. And what is this? Fundamentally, what is it? Yeah, right. Series. Yeah. So this is called the Fourier series. And why do we look at Fourier series? What is so special about the Fourier series? Some of you will know because you guys would have done a course on Fourier series like me. So what is so special about the Fourier series? Yeah, it's owned by Fourier, yeah, sure. But why did we name it? If this was a normal series, we would have named it. What is so special about this? Yes, exactly. So you can represent any periodic function in this. Any periodic, even complex periodic. You can represent it in this form. I'm not going to go to the proof of this. Even I do know the proof of this. But yeah, that is the special thing. And you as the session progresses, you're going to learn more about Fourier series. But something I wanted to just mention is that you're not going to learn it in this form, the form I've taught you, because this is the form which was best suited to solving differential equations. But a form which is more intuitive to you guys will be in terms of sine and cos. And so that is this form. Now, these two forms I claim are equivalent. And they are equivalent because of this proof. I'm not going to really do this proof, but it's suffice to say, exponentials can be broken in terms of cos kx and k omega t and I sine k omega t. So you just break it apart and you do some manipulation and you will get this other sort of function. It will be covered in depth later. So I'll just move to stop at this slide. So my part is done. The rest of the session will be taken by KK. We'll release the attendance form, the first attendance form. You guys can fill that up. So I'll stop at this slide. You guys can look at the proof if you want. Do you have any questions? Why is limits of k? Yeah, that is an interesting thing. It is different on both sides. Look at the proof. You can always contact me if you don't understand the proof. But yeah, the idea is you will actually break it into two different summations and problems. And that is actually important. It shouldn't be from minus infinity to infinity because you'll have some repeating terms if it's in cosine form. So, Sneha, is that fine? And have yeah, that will never happen. You will not have a small element. Not in this form. I mean, you can define it, but you will never use it here. So I need to show the note. We'll share this note. It's fine. Yeah, slides will share. As always, we'll share slides. It will be on our website. So any more doubts? You mean the exponential thing? Sahil, are you talking about the exponential thing? limits on, yeah, sigma. Which one? The exponential part or the cosine part? I mean, both. Okay, it doesn't matter. In both cases, no, it has to be from minus infinity to infinity. We define it like that. That is how we define it, so that we can deal with it. Because as the session progresses, we'll learn more properties about Fourier series, and there it is required that the limits are these, as I have defined. That's a clear. Come on, guys. I'll stay for another 2 minutes. Any more questions? Yeah, okay, here is an interesting thing. I'll tell you. So if you have limits from minus infinity to infinity, interesting thing to note is, in fact, it is true for any limit, because I can always see if I wanted to define it for k going from, let's say, minus 10 to 10. I claim this already encompasses that, because I can just say ak is equal to 0 for mod k greater than 10, right? And then you'll see these two are equal. So what you're asking is actually a special case of this main equation. So yeah, yes, you can. That's a clear. Okay, so you guys can always contact me personally. My number and all will be in the assignment. What is the real life? Okay, it comes about. Okay, the third part of this topic, Harith, is going to be about noise and noise analysis, and you will see why it comes in handy there, because it becomes much easier to work with. And it will come about in many places actually. Most of the times, at least the use I've seen it is in signals, analysis of signals and stuff. It comes about. Okay, so if there are no more doubts, I'll stop. I'll let KK take it.
Hey guys, can you hear me? Hello.
Yeah, we can.
Okay. So guys, welcome to my session, and I'll be talking about Fourier series again, as Achintya mentioned. Myself, Karthik Kashyap, a coordinator of the Math Club, and let's begin. As Achintya mentioned, Fourier series, we can represent it as a linear combination of sines and cosines only, and this is limited to only periodic functions. Not any random function, only periodic functions, and it is based on orthogonality relationships of sines and coses. This you can relate it to linear independence that he mentioned. We will get to that later on. So let's say there is a function f of x that is periodic over minus pi to pi, that is has a period of 2 pi. So we can write this in terms of the trigonometric Fourier series as a naught by 2 plus sigma from n is equal to 1 to infinity a n cos n x plus b n sin n x. In here, a0, an, and bn are coefficients corresponding to the given function. And we will be able to find this for any given function that is given. How we are supposed to find this? For this, we will need a few properties, and then I will be actually solving this in my tab. So I'll be switching to my tab view. Hopefully you guys can see this. So I'll be writing here and solving if any proofs are needed. So starting with the first property that we need to find integral of sine mx dx from minus pi to pi. So this we can say is the area of sine over minus pi to pi. This is sine function, right? And this is minus pi to pi. So we can say that the net area will be 0. It's pretty straightforward from JE. So we can say that this integral will be according to 0. And at m is equal to 0, the sine is itself 0. So integral is 0 again. So this integral, we can say that this is 0 for all m values. So moving on, the second property from minus pi to pi integral cos mx dx this time. Again, similarly, even this, if we plot it, okay, this is how it comes out. Again, similarly, the area again from minus pi to pi is 0 over here. But if m is 0, only in the specific case that m is 0, cos 0 will be equal to 1, in which integral of 1 dx from minus pi to pi will be equal to 2 pi. So we have to mention that specifically over here. So is equal to 0 for all m not equal to 0, and then is equal to 2 pi when m is equal to 0. We will need this later on these subcases. Yes.
Can you switch your color to white or something? Some people are saying it's kind of hard to see.
Okay, I'll see. Okay, is this fine?
It's fine. I guess.
Okay, so this is the second property that we have so far. We have taken integral of sine and integral of cos. So now for starting with the third one, let's take integral of sine mx cos nx dx from minus pi to pi, of course. For this, according to trigonometric properties, we can write sine cos in terms of sine c plus sine d, right? So we can just write this as sine m plus n times x plus sine m minus n times x divided by 2 dx. This is sine mx cos nx dx, right? So again, minus pi to pi. So we can split the integral in these two terms and take 2 outside as it is a constant. So we can get 1 by 2 times of integral minus pi to pi sine m plus n x plus, sorry, dx plus integral minus pi to pi sine m minus n x dx. So let's go over to the first property and check integral of sine mx dx from minus pi to pi is 0 for all m. So if we take this m plus n as some other m and this as some other m, we see that this is equivalent to the first property. So both these integrals turn out to be 0. So we can get this resultant as 0. So these properties, integral of sine mx cos nx dx from minus pi to pi is equal to 0 for all m comma n, because we didn't have any restrictions on sine. So that is the third property. The fourth one, in this case, let's take something like integral sine mx and sine nx dx from minus pi to pi instead of sine and cos. For this, again, similar transformation can be made. Integral minus pi to pi. Sine can be written as cos c minus cos t, right? So it is cos m minus n x dx minus cos m plus n, sorry, not dx, m plus n x divided by 2. This is our transformation, and dx outside for the integral, of course. So again, let's take the integral separately and take 1 by 2 outside. So we can write this as 1 by 2 of integral cos m minus n x dx plus integral cos m plus n x dx, again minus pi to pi. Now this is based on the second property that we are using. Let's move there. Integral cos mx is 0 for m not equal to 0 and 2 pi for m is equal to 0. So let's check there. Again, here, by the way, I need to mention m and n are greater or equal to 0 and are integers. So for that, let's look at this term first, the second term. If m and n both are positive, then this part cannot be 0, not 0 by the way, greater or equal to 1. There, starting from 1, they are integers. So this value can never be equal to 0. So this is the part of second property with m not equal to 0, you can say. So this part will be 0. Whereas this part, if m happens to be equal to n, this value will be equal to 0. So this integral will be equal to 2 pi. But if m not equal to n, whatever value it is, if it's not equal to each other, then this will be equivalent to 0, the integral that is from the property. So if m equal to n, this integral turns out to be 1 by 2 of 2 pi plus 0, which is equal to pi. And if m not equal to n, this happens to be equal to 1 by 2 of 0 plus 0, which is equal to 0 again. So this is this property. So last, we'll take cos mx, cos nx dx from minus pi to pi. We have taken sin and sin and sin and cos. Lastly, cos and cos. So again, this is the same transformation again, cos c plus cos d. So we can write this as integral cos m plus n x dx plus cos m minus n x dx. Sorry, I keep adding dx divided by 2 and then outside dx from minus pi to pi integral. So again, we can do the same, and this time we will get integral cos m plus n x dx plus integral cos m minus n x dx minus pi to pi integral. So in this case, we can see that this term is the one like last time, that will be equal to 2 pi when m is equal to n and will be 0 when m is not equal to m, and this term will always be equal to 0. So again, we can say similarly, I don't have to write it again. For m is equal to n, this turns out to be equal to pi, again 1 by 2 of 2 pi, and for m not equal to n, this will be equal to 0. So these are the properties that we will need to solve for the coefficients of Fourier series. So let's head back to my PPT. These are the 5 properties that we have proved so far. You can look at it. This is exactly what we have proved so far. So let's move on to actually finding the coefficients. So I'll switch back to my tab again. Let's start with how we define the Fourier series. We saw that it is defined as a0 by 2 plus sigma an cos nx from n is equal to 1 to infinity plus sigma bn sin nx from n is equal to 1 to infinity. So this is how we define Fourier series. By the way, we have a by 2 over here. Just remember this. We are adding this for convenience. We will get to why we are adding it later. But anyway, it is a constant. It doesn't matter if we divide by 2 or what. For now, let's keep it as by 2. So let's try to find a0 first. It is the easiest. So we have seen that integral of sine and integral of cos both are 0 when n is not equal to 0. So here as n not equal to 0 and this is anyway 0, we can just integrate on both sides from minus pi to pi. So if we do that, from minus pi to pi integral f of x is a0 by 2 is constant, so we can just write it outside, integral 1 dx from minus pi to pi, and then see all the ans are constant, all the bns are constant. So we can just take the integral inside the summation for each cos and each sine terms. So we can just write this as summation of n is equal to 1 to infinity of an integral cos nx dx from minus pi to pi plus bn integral sine nx dx from minus pi to pi. So this is what we get on just integrating from minus pi to pi. So let's write this. This we can just leave it as it is. And then this integral 1 is 2 pi. So a0 by 2 times 2 pi plus this integral. You see n is not equal to 0 anywhere. N is starting from 1 and going till infinity. So this integral will be equal to 0 for all n values in the summation. So each and every value in the summation turns out to be 0. Similarly, even this turns out to be 0. So this whole entire summation, all the terms are 0. So we can just write this as 0. And this is integral f of x dx from minus pi to pi. So cancelling 2, we get n. If we send pi on the other side, a0 is 1 by pi times of minus pi to pi integral of f of x dx. So for now, we have found one term of our Fourier series. Let's move on to, let's say, an. So going back to the Fourier series, in this case, we would want to find an. So let's just multiply a term cos mx for some m value, and let's see how it goes. F of x times cos mx is equal to a0 by 2 cos mx plus, let's take m as some constant for this part. So we can just send it inside the summation everywhere. So summation an cos nx cos mx, and n is the only thing that is varying inside the summation, because for this equation we have taken m as a constant. And again, summation bn sin nx cos mx. So again, let's integrate this from minus pi to pi. So with that, we get minus pi to pi integral of f of x cos mx dx is equal to a0 by 2 is constant. So keep that outside. A0 by 2 integral cos mx dx from minus pi to pi. And then again, we can take the integral inside because an and cos nx in this case are constant. So we can just write the summation an. Sorry, the cos mx is not constant. It is a function. So only an is constant. So we can just write an outside and cos nx cos mx dx from minus pi to pi, and then sigma bn integral similarly for sin nx cos mx dx from minus pi to pi. So we can see that over here that this is equivalent to the fifth property that we have proved, and this is equivalent to the third property that we have proved. And so this value will be always equal to 0. That is what we have seen. This is the second property. So this is equal to 0 as, let me mention, m starts from 1. So m is greater than equal to 1 over here. So this value will be equal to 0 anyway. So in this part, let's take this outside. So integral cos nx cos mx dx from minus pi to pi. If you want to talk about this, the only place where this integral is non-zero is where n is equal to m, right? Any other n value that we take, it'll be m is not equal to n, so the integral will become equal to 0. So only at this point is where it is equal to pi that we have seen. So the only value is when n is equal to m, that is non-zero. So that is the only part of the summation that we need to take outside. So if we write this as equality, the first term is 0. This is entirely 0. So we can write that as 0. And the only part in the second summation is a m and pi, the integral value itself, plus, and then this part, this summation is anyway 0 for all the terms. So this is what we get. So sorry, if we send pi on the other side, we get am is equal to 1 by pi times of integral f of x cos mx dx from minus pi to pi. So let's, for simplicity, replace m by n because it's a constant anyway. If we write an is equal to 1 by pi times of integral f of x cos nx dx. For this, we have found the value of an for all n. If you want any value of n, you can just substitute it in the cos and find the integral. So similarly, we can say for bn, I'll just write it directly. We can multiply it by sin nx this time, sin mx this time, and we can write it as integral sin mx dx from minus pi to pi is equal to a0 by 2 integral sin mx dx from minus pi to pi, and then summation an integral cos nx sin mx dx from minus pi to pi, and then sigma bn integral minus pi to pi sin nx sin mx dx. So similar to before, this value will always be equal to 0, and then this value is again always equal to 0 because it's sine and cos. And this value again, the only place where it is non-zero is when n is equal to m. So the only value again we get from this is bm times pi, the integral value. So bm, let's replace it by n. So bn we get as 1 by pi times of integral f of x sin nx dx. So this is the value of bn that we get. So we have found all the coefficient values corresponding to the given function. So moving on to the slides, this is what we have gotten so far. A0 is 1 by pi times of integral f of x dx, and an is 1 by pi times of integral f of x cos nx dx, and bn is 1 by pi times of integral f of x sin nx dx. So if you want to remember this, you can keep this as 1 by pi times of integral f of x times what the coefficient is multiplied by. So a0 is multiplied by cos nx in the Fourier series, so it is integral cos nx. Bn multiplied by sine in Fourier, so you can just take it as integral f of x times sine, and a0 is just a constant over there, not multiplied by any trigonometric property, so you can just take it as integral integral f of x dx. So notice how all of these terms have 1 by pi over here, even though we have taken a different case for a0 by 2. So that by 2 is the reason, so that this symmetry we can see. If we had not taken the by 2, we would get a0 is equal to 1 by 2 pi times of integral, which would be a little unsymmetric. So just for that convenience, we have taken a0 by 2 initially. Moving on. So now that we have found the Fourier series, how do we relate the original function and the Fourier series? Let's say our given function is f of x and the Fourier series that we have found is g of x. Now the Fourier series is just a linear combination of sines and coses. So as sine and cos both are continuous for all domain, we can say that the Fourier series is also continuous at every point. But the given function needn't be continuous at every point. So how do we relate this at points of continuity and points of discontinuity? At points of continuity, we can just equate the points, equate the values of the functions. F of x is equal to g of x. Simple. Now let's say there is a point of discontinuity in f of x at some point x0. What do we do at this? We cannot just take the value of f of x0 because it's not defined over there. It is discontinuous. So in this case, we will use limits. Should we use the limits on the right side or the left side of x0? We will use both. We will take the average on the both sides. So g of x is equal to half of limit x tends to x0 minus of f of x plus limit x tends to x0 plus of f of x. So I've added little extra constraints over here. That is when x0 is in between minus pi to pi and not equal to them. And when x0 is equal to minus pi or pi, then we have replaced a few things. I'll explain what it is. It's not very hard. So let's take the case of minus pi minus. So we are going to the left part of minus pi. So that is as f of x is periodic from minus pi to pi. The left part of minus pi is equivalent to almost the rightmost part of the previous periodic part. So for which we can say that that is almost equivalent to pi minus. As it is periodic, it is the same value anyway. Similarly, for pi plus, you can say that the right part of pi is equivalent to almost the left part of the next periodic part of this function. So we can take that as minus pi plus. So that is how we get the next part. When x0 is equal to either minus pi or pi, it is half limit x tends to pi minus of f of x plus limit x tends to minus pi plus of f of x. You don't really have to do this. It's just formally writing just to keep it in terms of like between minus pi to pi only and not go beyond that. So as I said, at points of continuity, they both are equal, then they coincide. And if it is discontinuous at some point, it is equal to average of the limits of at the point of discontinuity. Moving on. OK, this is the poll question. Moderators, please put the poll for this question. Let's say there is a given function f of x is equal to sine square x and from minus pi to pi. find the values of A0 and A2 specifically. And I would say, I would give you a hint actually, do not blindly integrate this with the identities that we have gotten so far. Try to somehow get it in terms of Fourier series. Okay, I'm going to go on with this. I'm going to assume you answered. I'll just go on to Teams and just check. And C got the most votes. So how I went for you to do this without actually integrating it, I'll just tell you the method. We write this in terms of cos 2x. We anyway want to write this in terms of Fourier series, that is give it in terms of linear combinations of sines and coses instead of it being sine square. So we can just write it in terms of cos 2x. Cos 2x is 1 minus 2 sine square x, with which we get sine square x is 1 minus cos 2x by 2. With that, we get A0 value as 1 by 2 and A2 value as minus 1 by 2. So option D is actually the correct answer. Yes, Mishra, I will get to the point of even and odd functions. That is the next part of this. Okay, moving on with this. Let's say for now we have seen about properties of Fourier series, properties of functions which are periodic on only minus pi to pi. What if we have a different generalized periodicity like minus L to L or something? So I'll switch to my tab again. So we don't have to do everything again. We just have to modify the original Fourier series to be able to accommodate for this new periodicity. So we take f of x is a0 by 2 plus sigma an cos nx plus sigma bn sin nx. We should be able to change this periodicity from minus pi to pi. Let's say x belongs to this to minus L to L to y. So x by pi belongs to minus 1 to 1, right? And similarly, y by L belongs to minus 1 to 1. So we can say that x by pi is equivalent to y by L. So to change it to in terms of y, that is what we need in terms of minus L to L. We can just take y is equal to Lx by pi. So again, if we want in terms of dx, if we want to replace x by y, we need x value also. X is equal to y pi by L. And then dx is equal to pi by L times of dy. So everywhere we see x, we can just replace it by y pi by L, and we will get our modified function. So f of x instead of that f of y is equal to a0 by 2. This is common anyway. So plus summation an. These are all constant anyway. N is equal to 1 to infinity cos it was nx. We would replace that by n y pi by L, or more formally n pi y by L. So this is for cos, and similarly for sine, we can write it as sigma bn sine n pi y by L from n is equal to 1 to infinity. So this is our modified Fourier series for periodicity of minus L to L. Now again, we don't have to find the coefficients again manually. We can just use the same thing method again. A0 is integral 1 by pi times of integral f of x dx, right? From minus pi to pi. So again, we have to just replace x by y. So 1 by pi times of integral, the limits changes again. Y is equal to Lx by pi, right? So as x is from minus pi to pi, y is from minus L to L. So the limits are minus L to L changed, f of y, and dx we have seen here to be pi by L times of dy. So pi by L times of dy. So we can just cancel this and then take 1 by L outside, integral minus L to L, f of y dy. So it is almost the same, it's just pi is replaced by L everywhere in the coefficients. So if we talk about En on the other hand, it is 1 by pi times of integral f of x cos nx dx from minus pi to pi. I won't go over this manually again. We would get, again, this part would be the same, 1 by L, and then limits again 1 minus L to L, f of x, f of y, and then cos nx. We have seen the transformation in the Fourier series itself. We can just replace the same thing, cos n pi y by L. This is what we got before, and then dy. So this is the modified an expression for the generalized periodicity. Again, I am not going to do this. You can just say the same thing, analogy, minus 1 by L times of integral minus L to L, f of y sine n pi y by L dy. So this is for modified periodicity. There are other properties like when you shift the periodicity by some x naught or something. I'm not going to go over that. You can do the same. It is again f of x is a naught by 2 plus summation an cos n pi x by L and summation bn sine n pi x by L. So again, a naught also just replace pi by L. This is what we got. So moving on, even and odd functions. So this is not really a major topic. This is just a more simplification when the given function is even or odd. So we have seen in JEE that integral of an odd function will give an even function, right? So as a property of definite integrals, integral of an odd function from, let's say, from minus a to a will be equal to 0 because that will be equal to even function with the limits minus a to a. So even of a minus even of minus a. So I'll just write it just to show integral of odd function dx from minus a to a will give some even function with the limits minus a to a. So this is even of a minus even at a minus even at minus a. As it is an even function, even at minus a is equal to even at a. So this is equivalent to even at a itself. So these both cancel out. This will be equal to 0. Similarly, minus a to a integral even function will give an odd function. So we can just write this as 2 times of 0 to a and even integral dx. So these are a few properties that we have seen in JEE itself, pretty standard. We can extend it on to this coefficients as well. Now, suppose f of x is an even function. So let's look at a naught. Before that, let's look at bn. So we can get 1 by L times of, let's take it from minus pi to pi, just to show integral minus pi to pi integral f of x sine nx dx. So we know that sine is an even function, an odd function, and this f of x we have taken as an even function. So this is even and this is odd. So an even function times an odd function will be equal to an odd function. So this whole thing is an odd function. So again, this is equivalent to our previous assumption at integral odd function from minus a to a, in this case, a being equal to pi. So this integral we get as equal to 0. So bn is equal to 0 for all n values when the function is even. And similarly, we can do the same, this property as 2 times of 0 to a for a naught and an. So we get 2 by pi of integral 0 to pi f of x dx, and then an is equal to, again, similarly, integral 2 by pi times of integral 0 to pi f of x cos nx dx. Wait, before that, let's do it for even odd functions. So f of x, let it be odd. So in this case, let's take an integral 1 by pi integral minus pi to pi f of x cos nx dx. So cos is an even function and f of x we have taken as an odd function. So again, odd times even gives an odd function. So this whole thing is an odd function, integral of an odd function. So this will be equal to 0 this time. So again, similarly, if we take a naught, then that will be 1 by pi times of integral minus pi to pi f of x dx, and f of x is odd anyway, so the function is odd, so this will also be equal to 0. So bn, if we take f of x sine, in which case both are odd, so an odd times odd function times odd function is an even function, so the whole function is an even, so we can just write it as 2 by pi times of integral 0 to pi f of x sine nx dx. Again, this is not that important as properties, but these are just for simplification. We can use at a few special functions when the function is even and odd. So as we have seen, when the function is even, we get bn is equal to 0. So this function is only in terms of causes. So we call this a cosine series. So when the function is odd, an is equal to 0 and a naught is also equal to 0. So it is only in terms of sines. So this is called a sine series. Again, these are we have derived. So again, this is a little less known Fourier series. Achintya has talked about how we can show these terms in terms of e power I theta, that is sine and cos. E power I theta is equal to cos theta plus I sine theta. So this trigonometric Fourier series can also be expressed in terms of e power I thetas, just e power I thetas. So this is what we get. This is what Achintya has also explained. This is also something that we'll be just showing. I won't be doing much on this. So going over this, we can get the coefficients as this. I won't be proving this. You can do this. It's the exact same proof that I have done for trigonometric series. Nothing changed. It's just different representation. That's all. So, and then because these two are related, the Fourier series in the trigonometric and the exponential are related. We get one from each other. So we can relate the coefficients as well. And we get this. Again, I'm not going to prove this. This is pretty straightforward itself. And then again, generalized periodicity. Again, even this I am not going to prove. It's the same proof as trigonometric series. We get f of x is an e power 2 pi I pi x by L instead of just I x, I n x. And then coefficients again minus 2n I pi x by L instead of just minus I n x. And then limits from minus L by 2 to L by 2. So before this, let's see a few properties. Actually, before seeing the properties, let's post the attendance. So moderators, please post the attendance for this, the attendance part 2. Okay, I'll show the slide for exponential Fourier again. If you have seen this, I'll move on to the next one. Again, the coefficients are this. You can just have a look at this and try to prove it is the exact same proof as the trigonometric series. Okay, I'm hoping all of you have filled in the attendance. If you have not, please fill it fast as it will be closed in a few minutes. So let's move on to the properties of Fourier series. I'm going to discuss just a few properties and not going to go over the proof. Again, it is pretty simple. So let's say there are three functions given f of x, g of x, and h of x, and the corresponding Fourier series, the exponential is an, bn, and cn. So for this, the first property is linearity. Let's say h of x is equal to a f of x plus b g of x. That is a and b are some constants, and h of x can be represented as linear combination of f of x and g of x. With this, we can directly equate the Fourier series coefficients as Cn is equal to a times bn plus a times an plus b times bn. So this follows linearity. So reversal. So let's say f of x and g of x are such that g of x is f of minus x. So again, we can obtain b of n by just equating it to a of minus n. That is reversing the order from which you are taking them, just like how we are reversing the axis. So this is also simple. Now let's say we have shifted the axis a little bit. Let's say g of x is f of x minus x naught. That is, we have shifted the function by some x naught, with which we get a constant out, that is e power minus 2n pi x naught by l. Notice this is a constant and it is not x, it is x naught. So with this, we can get bn is equal to an times e power minus 2n pi x naught by l, just multiplied by a constant. Again, if multiplication h of x is f of x times g of x, this is a little hard to visualize. Let's say there's two exponentials, e power I n1 and e power I n2, both from different a and f of x and g of x. Now, suppose you want to find for e power I n. So for that, you need to get, let's say, n1 from a. So what you have to get from B is n minus n1 contributed to this such that the multiplication gives e power n. So sorry, e power I nx. So for that, we have this summation such that the sum of subpoints L and n minus L gives the summation as n. So in a summation from L is equal to minus infinity to infinity, AL, B, and minus N. That is equal to Cn. So it's not very hard to prove. You can do it. I'm just going to mention it as it is a property. Now we have an example problem that we will solve using the Fourier series that we have learned so far. Let's say there is a function f of x that is equivalent to -1 when it is from minus pi to 0 and 1 when it is 0 to pi. Of course, this is a periodic function and I mentioned only the values from minus pi to pi. So after this, again, it goes on like this itself. So we have to find the Fourier series coefficients for this function. Let's do trigonometric, and we have to also find the value of this summation that is mentioned. First, we'll find the summation and see how we can get to this. Sorry, first we'll get the coefficients for a series and we'll see how we can get to this summation from that. So I'll switch to my tab. So given function is f of x is -1 from minus pi to 0 and 1 from 0 to pi. So for this, let's say a0 is, before that, we can notice one thing. This is an odd function. That is at f of x is equal to minus f of minus x, because let's say x greater than 0, this value is equal to 1 and this value is equal to -1. So yes, this is an odd function. So we don't need to directly find a0 and an. We can just say both of them are 0 for all n values. Similarly, bn, we can just take that as 2 by pi times of integral 0 to pi f of x sine nx dx. So if we substitute 2 by pi integral f of x from 0 to pi, notice it is always 1. That is what it is, 1 from 0 to pi, and our limits are 0 to pi anyway. So f of x is always equal to 1. So this is just integral sine nx dx from 0 to pi. So 2 by pi into integral of sine is minus cos nx by n from 0 to pi. So 2 by pi outside, if we substitute, we'll get minus cos n pi plus cos 0 by n. So if we take n outside as well, because it is a constant for this, so 2 by n pi into 1, that is cos 0 minus cos n pi. This is bn. Now let's try to simplify this even more. What values can cos n pi take? Cos 1, sorry, when n is equal to 1, cos pi is equal to -1. And when n is equal to 2, cos 2 pi is equal to 1. Cos 3 pi when n is equal to 3 is -1. And cos 4 pi when n is equal to 4 is 1. So with this, we can say if n is odd, cos n pi is -1. And when n is even, cos n pi is equal to 1. So let's do this for two subcases. Let's say n is odd. For this, bn is equal to 2 by n pi times of 1 minus cos n pi, which is equal to -1. So minus of -1. So this will be equal to 2. So this is 4 by n pi, bn value. And when n is even, we get bn is equal to 2 by n pi of 1 minus cos n pi, which in this case is 1. So this is 0. So bn is 0 when n is even. So writing this, we get a0 equal to 0. Sorry, an equal to 0, and then bn is equal to piecewise 4 by n pi when n is odd and 0 when n is even. So these are the Fourier series coefficients. We have successfully gotten the first part of the question. Now the second part of the question, they have asked us to find this summation n is equal to 0 to infinity minus 1 power n by 2n plus 1. So let's try to find that using this Fourier series. Because they haven't mentioned anything, we should assume that we can obtain it from this Fourier series. So let's just write Fourier series based on these coefficients: sigma an cos nx plus sigma bn sin nx. So an, a0 and an both are 0. So these parts are zeros, and then sigma bn sin nx from n is equal to 1 to infinity. Let's split this into two summations. N is equal to 1, 3, so on. That is n is odd till infinity. Bn sin nx plus summation n is equal to 2, 4, so on, even till infinity. Bn sin nx. So we have split this into n is equal to even and n is equal to odd. So we have seen that Bn is equal to 0 for all n is equal to even values. So this is 0. So this entire summation will be equal to 0. This summation, on the other hand, Bn is equal to 4 by n pi for all n is equal to odd. So as it is a constant, we can just take it out. N is not a constant. Only 4 by pi is constant. So 4 by pi times of summation n is equal to 1 to infinity for only odd values sin nx divided by n. So this is what we have obtained so far with the Fourier. Let's try to simplify this even more. Let's say we want to have this in terms of only n is equal to 1 to infinity or 0 to infinity instead of having it only odd. So let's try to write this in terms of odd function, an odd number. So if we replace this by 2n plus 1, where n is equal to 0 to infinity, or let's use a different variable, 2k plus 1 from k is equal to 0 to infinity. So this changes the summation 4 by pi times of integral k is equal to 0 to infinity, not 1, because that is where it starts. When n is equal to 1 to infinity and odd, k starts from 0 because k is 2k plus 1. So summation k is equal to 0 to infinity sin n is 2k plus 1 times of x divided by 2k plus 1. So this is the simplified Fourier series that we have obtained so far. Now for simplicity, we can just replace this k by n everywhere because that is what the question asked us to find. So n is equal to 0 to infinity and then 2n plus 1 and 2n plus 1 everywhere. And what we need, that is required summation, is summation of n is equal to 0 to infinity minus 1 power n divided by 2n plus 1. What value of x can we substitute in this f of x such that the sign term can vanish? That is, there would be no sign terms and it would be just a value that we know of, and hopefully as only minus 1 and 1 terms. This value for sign would be x is equal to pi by 2. So if it is sin pi by 2, it is equal to 1, sin 3 pi by 2, it is equal to minus 1, 5 pi by 2 is 1, and so on. So let's put x is equal to pi by 2 in this Fourier series. We'll get pi by 2 is equal to 4 by pi times of summation n is equal to 0 to infinity sin 2n plus 1 times of pi by 2 divided by 2n plus 1. So this is what we get. Now we know that function is f of x is equal to 1 for all values from 0 to pi, and pi by 2 belongs to 0 to pi. So this value is equal to 1, f of pi by 2. So we can write 1 is equal to 4 by pi times of summation n is equal to 0 to infinity sin 2n plus 1 pi by 2 divided by 2n plus 1. So we can send this pi by 4 on the other side because it's a constant that is multiplied. Pi by 4 is equal to summation n is equal to 0 to infinity sin 2n plus 1 times of pi by 2 by 2n plus 1. Now let's see sin pi by 2 is equal to 1, sine 3 pi by 2 is -1, sine 5 pi by 2 is 1, sine 7 pi by 2 is -1. So in this case, n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. So when n is even in this case, we get sine value equal to 1, and n is odd, we get sine value equal to -1. So we can write sine, I'll just write it in the next line. So we can just write sine 2n plus 1 times of pi by 2 as -1 power n. That is, when n is even, -1 power n is 1. And when n is odd, -1 power n is -1. So we can just replace this over in our equation 1. So pi by 4 is equal to summation n is equal to 0 to infinity. And then sine value is replaced by -1 power n. So -1 power n divided by 2n plus 1. So this is the summation that they have asked for. So we have obtained that the value that they need is pi by 4. So this is how we solve Fourier series questions. So moving on again, as you have seen, n is 0 for all n because it's an odd function, and then bn is 4 by n pi when n is odd and 0 when n is even, and Fourier series again 4 by pi times of integral summation n is equal to 0 to infinity sine 2n plus 1 times of x by 2n plus 1. Now we can also solve this in terms of exponential Fourier series. Again, the method is exactly the same because it's just a different representation of the same thing. So we will get this, and summation again we got it as pi by 4. So we have solved this question. Now that we have seen theoretically how Fourier series works, how does this actually match up to the actual function? Now you guys had Octave in the previous session of MATLAB, so I'm going to assume you guys know how MATLAB works and all of that. So I'm not going to actually write a code. I'm going to show you the code that I've written and what each part does. So this is the code I have written to solve this question of Fourier series. That is, f of x is -1 when minus pi to 0 and 1 from 0 to pi. So this is where I've defined this function x is equal to g of t is when x, this value gives 1 when it is from 0 to pi, and then -1 from minus pi to 0. It's just taking modulus, and based on that, if it is less than pi or greater than, greater than pi, it gives the required value. So you don't have to worry about this.
Slightly zoom in the screen. People want to see the
Okay.
code.
I'll just take this to full screen. Okay, I think they should be visible now. So this part, just zoom in even more. So this part, this function gives the function that we need, and this x is equal to f of t comma n gives our Fourier series representation. So I added another extra input as n, being the number of terms we are adding to this Fourier series. So for I is equal to 0 to n minus 1, that is n terms, I am adding 4 by pi times of sine 2n plus 1 times of t by 2n plus 1. This is the Fourier series that we got anyway. So starting with 0, we get this as our Fourier series expression for n terms. Ideally, as we know, n goes from 0 to infinity, but just for representation, as computationally it is not possible to have infinite terms, we are going to see for each terms how it is possible. So let's start with n is equal to 1, that is just one term, and plot this. These are all functions for plotting it from x is equal to -6 to 6, just so it is easier to view. So if I run this, it shows just like this. This, as it is one term, is just one sine term. So it's just one sinusoidal wave. And it is not exactly the same as our original function. This blue part is our Fourier series and the red part is the actual given function. So for n is equal to 1, we are not getting very satisfactory results. Let's shift it to n is equal to 3. Like this, we get a little bit of this type of graph where it is kind of oscillating between this value of the actual function itself. Let's go even more terms, like n is equal to 5. Again, the same thing happens, but with more crescent tufts. N is equal to 10. we get again same more of this. So we are getting more and more crescent troughs for increasing terms. So let's directly jump to n is equal to 100 instead. Now in this case, we see that the number of crescent troughs and the amplitude of each crescent trough is so small that here almost we can see that here we cannot distinguish between the actual function and the Fourier series function. So this is almost the same already for just 100 terms. And we know that as terms keep going on, the contribution keeps going less because n is in the denominator. So let's add like 1000 terms this time. And in this case, we see that it's almost indistinguishable, only some slight parts at the endpoints that we can see a little blue dots, but except that there is almost no difference that we can see between the actual and the Fourier series. And this is for just 1000 terms. For infinite terms, it will be exactly the same. That's what we have seen. And again, I have made another octave function to actually plot the values as an animation from starting from n is equal to 1 to like 1000. So I'm not going to run this. I have a video over here. Let's pause this and start from the beginning. Again, this is for n is equal to 1, as we have seen. If we play this, we see that for increasing number of terms, it starts being almost linear at the midpoints, and at the points of discontinuity, it is like oscillating between equal and unequal. And as you have seen at 1000 terms, it becomes almost equal. So with this, we have seen that this is almost identical. So moving on with the next one, a few applications. This is Fourier series is, as Achintya mentioned, used for solving the differential equations, and Naveen will talk a few more applications of this. But other than that, signal processing, filtering, noise removal, this is what Naveen will talk about in the next session. And then I'll give you a brief introduction to Fourier transform. So far, we have seen Fourier series, and we can represent it in terms of sines and cosines, a linear combination for only periodic functions. How do we extend this to non-periodic functions? Let's see non-periodic functions first. Let's take the non-periodic function as a periodic function with a time period of infinity. That is the whole function as one whole period of the function. With this, we can take it as almost a periodic function with the time period tending to infinity. So what we can do for Fourier transform is we can just take this as an extension from Fourier series with just period tending to infinity, as this says. So with this, I am not going to solve it. We get this as the Fourier transform. This term is the Fourier transform over here. Instead of an, bn, and all of that, we get f of omega. That is in terms of the frequency. And this is from minus infinity to infinity omega instead of just integers in the Fourier series. So we can find the Fourier transform and the inverse Fourier transform as well. Now this, the important thing to talk about here is f of x, the small f of x, the actual function, and the Fourier transform, the capital F of omega, give the same information about a signal, a function, but in just different representation. F of x, the given function, takes the domain as x, whereas the Fourier transform f of omega takes frequency as the domain. So it's just different representation that we get of the same function. And now we will be talking about this. So I had to introduce this. So as I have not done much, I have attached a reference if you want to check out this more. And with this, I am done with my session. Thank you for listening. Naveen will be taking over this session from now on, and he'll be talking about root finding, removal of noise, and such. Thank you. And if you have any doubts, you can ask. I'll be there for about 2 minutes. Any doubts you have related to this session on the Fourier series, you can ask now. Okay, I assume you guys have no doubts. So I will let Naveen take over.
Hello guys. I
Just
hope
1
I'm
minute.
audible. Yeah.
Can you take up the summation example once again? Someone in YouTube is asking.
Right. I think what we can do is we can share an explanation to the summation on YouTube later. We are currently slightly running short of time. So I apologize for that as well. I think today's meeting might go on till 11:20. 1:15. So we need to keep going. So sorry for that. Okay. I hope my screen is visible and I am audible. And someone confirm. Am I? Okay. Right. So let's begin. Hello guys, I'm Navin. I'm also coordinator of the Mathematics Club. And today I'll be briefing you a bit about the basics of Fourier transform, left off where Kashyap had taught you. And after that, we'll be implementing everything that we have learned in GNU Octave. So let's begin. And here is our journey through Fourier tables. Now, you might have heard Kashyap refer to something. He had said that the Fourier transform of the function and the function represent the same information. And in some sense, that is true. Whatever information you can obtain about the function from, say, f of x, I'll call this f of x as f of t and call it the time domain representation of the function. You can get the same amount of information from the frequency domain as well. So what do these two things actually represent? What you are actually seen till now is the time domain representation of the function, where say you put t equals some value t naught, the value f of t naught that it gives is the actual value of the function itself. It gives you the amplitude of the function at that given time instant t naught. But there's another way of representing this. You can think of the same function as being composed of infinitely many sinusoids interfering with each other, sort of like when you go to the beach and you see a lot of waves coming crashing to the shore. There would be some waves which win over others. They would be interfering with each other, somewhat constructively interfere, somewhat destructively. But at every point of time, at every place, there would be some amplitude. And that amplitude is essentially the summation of various waves interacting together. So what f of omega represents is the strength of the particular sinusoid e power I omega t, which is just a fancy way of representing the sine and cosine package together, that contributes to the overall signal. So a way to visualize this is something that I'll attempt to draw here. You can think of the function as something like being composed of infinitely many tiny stems. So for example, let's say we have these two stems. So when these two stems add together, what you get is something here and something here. And I recently found a very good article. I'll be sharing this to you as well, which represents functions as vectors. And you can see how as you increase the number of stems, the representation that you get is the actual function itself. So what happens here is we have many vertical stems, each of them spaced apart, which take values only where they are present and everywhere else they are 0. When you add all of them together, you get the original function back when you tend the number of stems to infinity. Now, the same way, what you can do is you can take infinitely many sinusoids with every possible frequency from minus to infinity, scale each of them by some factor, and when you add them all together, what you get is the original function itself. So that, in a sense, is what f of omega represents. F of omega is the strength of that particular sinusoid with frequency omega equals, say, some omega naught. I hope that is clear to everyone. So let us take an example. Say we have the function f of t equals sine pi t that in time domain would look something like this. At every time instant t, what you will be getting is the value of the function at that particular point. Now, if you try to represent the same thing in frequency domain, what you can do is decompose the sine into exponentials using Euler's formula. And what you'll be seeing here is it only contains two frequencies, one at omega equals pi and one at omega equals minus pi. So the Fourier transform representation that is in the frequency domain would look something like the graph shown here. You'd see two spikes at omega equals minus pi and plus pi because that's where the information is, and everywhere else the function would be 0. Now, this is not entirely the accurate representation. If you were to actually properly represent it, what you'll be getting is something known as a Dirac delta, whose actual value would be something around infinite, but when you integrate it toward the domain, you'll get finite values at minus pi and pi. That is not something I'll be explaining a lot here, but this graph provides you a pretty intuitive and visual explanation of how the function would look like. Now, I'd also like to talk about some two important functions. One of them being the rect of x, also known as the rectangular pulse. What this function essentially is it has an amplitude of 1 from x equals -1 to +1. Sorry, x equals -half to +half. You can always scale x to increase the duration. And the function is 0 everywhere else. That is, rect of x equals 1 when x lies between -half and +half, and rect of x is 0 everywhere else. Now, one more important function is the sinc of x. That is sine pi x over pi x. Some people do not include the pi factor, but that is fine. You can always scale it down. The purpose for putting the pi factor is here due to some normalization reasons. If we put it this way, then pretty good integral takes a pretty good value. That's all I'd say. So where would you encounter these functions? The answer is in signal processing and in a lot of physics problems. So these functions are something that you would find hidden in nature a lot. A rectangle of x is something that you can use to restrict some function within a particular domain. And the sinc of x is something that you'd find comes out naturally in something like, let's say, interference. A lot of you would have probably studied interference in grade 12. And there you'd have seen that the intensity of the light interfering at some point on the screen is proportional to sin square x by x square. So that is what the sinc function is. And why am I talking about them here? These two particularly, it's because they are Fourier transforms of each other. In the sense, if you take the Fourier transform of the rectangular pulse, what you get is the sinc. If you take the Fourier transform of the sinc, what you get is the rect. And now this is not something that's unique to the rectangular pulse or the sinc itself. There's actually a more very general property that is known as duality. So let's say there is some function f of t. When you take the Fourier transform of this function, what you'll get is f of omega. And this f of omega is the Fourier transform of f of t. Now let's say you take the function f and represent it, not represent it, you take the exact same function, but instead of taking the domain as omega, you take the domain as the time space again and take its Fourier transform again. What you'll be getting is 2 pi times the original initial small f function with the input as minus omega. And how is this so? This is something that you can prove by using the formula for Fourier transformation that Kashyap had shown before. That's given here as well. You can simply plug in f of t once, get f of omega, and once you get f of omega, plug that into the Fourier transform process once again, and what you'll end up getting is this. This property is essentially a consequence of orthogonality, and any transformations that are orthogonal when applied twice lead to results which look similar to this. And one very important application of this is, quite interestingly, the uncertainty principle, something that you have seen in quantum mechanics, I presume, or probably in grade 11 chemistry. So you'd have heard about the Heisenberg's uncertainty principle, which states that the uncertainty in momentum and position when multiplied together is greater than some factor, if I remember correctly, h by 2 pi. So that is something you can prove using Fourier series. Fourier transforms. Also, you would have noticed here that the rectangular function is something that is limited within the duration x equals -half to +half, and it's 0 everywhere. So in some sense, the rectangular function is not that is spread out throughout the time domain. But when you look at its Fourier transform, the sinc, what you notice is the amplitude actually never dies out. It's only when you tend x to infinity that the function becomes truly 0. Even say you take some pretty big value, say x equals 1 million, you'd always get some value that's slightly greater than 0, but it's not exactly 0. So if you actually go ahead and compute the variance of the Fourier transform function and the function itself from -infinity to infinity and multiply them together, what you'll get is a more general result known as the frequency time uncertainty principle, I think. And that is something which is entirely mathematical, does not make any assumptions in physical reality, but still, through entirely mathematical means, you can still arrive at the uncertainty principle. So that is something that's quite amazing, if you ask me. All right. So I hope all of you are here with me and don't find this a lot confusing. So I think I'll stop for a minute or so and see if there are any doubts in Teams. At the same time, I think we can take the third round of attendance. All right. Aditya, so as I said before, the rectangular and the sinc functions are something that come up a lot in a lot of physical problems. So a particular reason for their existence is simply the relevance in the world that we live in. And one more important application is in signal processing. There are a lot of filters like say high pass, low pass, Butterworth, and so on. And all of these filters can be represented in some domain in terms of these, either the sinc or the rectangular ones. So, chat mods, you guys can put the attendance forms now. The third round, that is. I'll be waiting for that. Yes, Aditya, you're correct. These pulses are often used to define other functions. At the same time, it's also quite interesting to just learn about the functions themselves. They also have some pretty interesting properties. So I'll wait till 12:40 and I'll continue. In the meantime, I can clarify any doubts that you guys have. Right. So the way we can try to visualize the uncertainty principle is an example that I gave is the rect and the sinc function. We see that the rect function is bounded in time domain. It only exists for -half to +half and it's zero everywhere else. But the sinc function is something that splits out from -infinity to infinity. So whenever you try to find the Fourier transform of a function that is limited in one domain, in the other domain, it will always spread out from -infinity to infinity. This is something you can prove through rigorous means. And the consequence is, when you try to find the variance of these functions from -infinity to infinity, the one that is spread out will have a larger variance and the one that's limited will have a smaller variance. But it just so happens to be such that the product of these two variances is always greater than a particular quantity. And that is how you can arrive at the uncertainty principle. If you take a few courses in physical chem, you get to know that the momentum and position representations of the wave functions can be interchanged using Fourier transforms. So that is how the position velocity or position momentum uncertainty principle comes out to be. But at the same time, you can use it to any two quantities that are Fourier transforms of each other. I hope that clears it out. So considering its time, I'll move ahead. Fine. So one pretty important thing to look at is what's known as Parseval's identity. So if any of you are wondering what that is, it's Parseval, French mathematician. Yeah, that was my attempt at a pun. But on a more serious note, what Parseval's actual identity is what is given here below. It says that the absolute integral of f of x of t squared, that is integral from minus infinity to infinity, x of t squared dt, is 1 over 2 pi, the same integral, but the function represented in frequency domain instead of time domain. So how is this important? Well, it's a pretty useful tool which helps you in calculating integrals. So, for example, we'll have a pole here. Using Parseval's identity, which is shown here, can you find the value of the integral minus infinity to infinity sine square pi x by pi square x square dx? Now, if you go on actually computing this using standard means, it will take a lot of time. But if you use the fact that the Fourier transform of the rectangular pulse is the sinc function and use the identities given above, then it will be pretty easy for you. So chat mods, please put a poll. Now, while you guys are figuring out the integral, I'll also try to give an explanation of why this identity holds. So one way you can think of it is, say you figure out the Fourier transform of the function f x of t. What you can also do is figure out the Fourier transform of x conjugate t, that is x star t. And you guys would know that the product of x and x conjugate gives you mod x square. Now, when you multiply the same Fourier domain on both, you take the two integrals, multiply them together, what you get will be a product of two integrals. Now, using Fubini's theorem and all that, what you can do is basically eliminate the exponentials that show up, and what you get is an integral that's purely in the Fourier transform of x of t. So, if you carry out that proof, what you get is Parseval's identity. If any of you guys are curious and want a rigorous set of assumptions under which this holds true and so on and so forth, you guys can always reach out to me later on. I'll be happy to share you some relevant resources, or I'll probably prove it myself. So, did you guys figure out the value? Seems C has the majority response, and you guys are correct. So the important fact to have been used here is that the area of the rectangular pulse is 1. The area of the rectangular pulse squared is also 1. And when you apply the Fourier transform, what you get is 1 over 2 pi times the actual sine pi x over pi x that's mentioned here. And so, no, not 1 over 2 pi. If I remember correctly, I think. All right, there is some constant factor which I don't remember right now, but the answer is 1. So essentially, you compute the Fourier transform of the rectangular pulse. What you get is this integral, the function inside the integral. And when you use Parseval's identity, you can easily find out the answer and arrive at the option C, that is 1. And now, one more thing. An important thing to look at is, since this Fourier transform seems to be such a powerful tool, is there any catch? If you ask, then the answer is yes. It only exists for certain functions in the real and complex field. And the conditions given here are what are known as Dirichlet conditions. They are not necessary, but they are sufficient conditions for the Fourier transform to exist. So, what you'd be seeing is, say, I have written here integral x of t e power minus I omega t dt. So that is the formula for the Fourier transform of the function x of t. Again, the limits are from minus infinity to infinity. I have not mentioned that here. So you can use a triangle inequality to arrive at the inequality that it's less than or equal to the integral of the modulus of the function itself. And the modulus of e power I omega t is 1. So what you arrive at is this. So all right, it seems I made a typo. It shouldn't be square integrable. It should be absolutely integrable. So as long as s of t is absolutely integrable, the Fourier transform would exist. And at the same time, what we want is there shouldn't be any finitely many extremas in a given interval. So for example, there's a function known as Dirichlet's function q of x, which is used as a tester for whether a function is a number is a rational number or not. It takes in a real number and hands you out 1 if the number is rational and hands you out 0 if the number is irrational. So it's very easy to see that this function is extremely discontinuous. And if you try to represent it in terms of, right, what is easy to see is that it's discontinuous and it's more involved, but you can always show that whenever you try to find the Fourier transform of this, what you'll be getting is some nonsense that wouldn't be actually representing the function itself. So these two are some conditions, that is absolutely integrability and having finitely many extremas in any given interval, which ensure that the Fourier transform of the given function exists. There are some functions where these conditions are not met, but yet the Fourier transform exists. So in that sense, these are sufficient, but not necessary conditions. I hope that's clear. Now, moving on. All right. So here is where we'll be writing actual code on GNU Octave. But I think the time now itself is 11:50. So what I'll be doing instead is running you through some code that I've already written, explaining it. And if you guys want any more elaboration, I'll be happy to provide that on the WhatsApp groups. So before that, let's have a slight recap of the root finding methods that we had seen before. One of them is Newton-Raphson. What you do is you pick an initial guess, you draw a tangent to the function there, and wherever the tangent meets the x-axis, you move the predicted root there. And the essence behind this idea is if the iteration were to reach the actual root itself, then the tangent would basically intersect the x-axis at where it begins because it's at the root. It's by definition. So it is this property that essentially helps Newton-Raphson to converge. Now, one more method that we had seen is bisection, where we created a bracket within which the function could lie. And within that bracket, at the midpoint, we assume that the root existed. And by checking the functions of the sign of the function at the left boundary and the right boundary, we tried to narrow down the bracket and get a more refined guess of what the root could be. So if you guys want a visual explanation, I have written some, I've made a tiny thing in Desmos, and I'll show that to you guys. So how the Newton-Raphson method works is this. We start off here, we draw a tangent, it intersects here. So as you improve the iterations, what happens is we start off the tangent drawing process at the point where it cuts the x-axis before. Now, continuing this, what essentially happens is we finally converge. Now, in 4 iterations, you have gone this close to the root. If you increase the number of iterations, you'll get more and more accurate results. At the same time, how the bisection method, that is the bracketing method, works is something like this. You start off with an interval, a guess interval where the root could be, and then you try to narrow down where it might be. And within, say 10 iterations, the root actually converges. And how do you actually narrow down the root? What you see is, say, take for example here, the value of the function at x root is positive, and at x right is also positive, whereas in x left it's negative. So you know that the x right can be moved even further closer, and even then, to the new x right, f of x right and f of x left will be of opposite signs, so you can be sure that there is a root in between. So these are the 2 methods that we had seen before, and I'll show you the implementation of the same processes in Octave. Not exactly Octave, I'll be using MATLAB, but you guys should be able to use the same code there as well. All right, so here is the code for root finding. I hope the screen is clear. If you guys want me to increase the font size or something, let me know. All right. It's clear, right? Fine. I'll proceed. So what I have in there are some functions that I've defined first. The first one being f of x. So it takes an x as the input. The function is called f, and the output is y. And what I do is set y to x square minus x cube plus 3x plus 2. This is just some example function. You can plug in whatever function you want. And you might also be seeing this dot being present here. So what this dot does is something known as broadcasting. So say you put the value of x as 1, it will actually square 1 minus 1 plus 3 plus 2 and do all that. But even if you pass in an array instead of a single number into x, what the broadcasting operator will do is pass on this operation to every element inside the array. So let's say you have an array 1, 2. What this broadcasting operator will do is apply the same operation on 1 and 2 as well and give you a new array which contains f of 1, f of 2. At the same time, using the standard rules of differentiation, I've also figured out df by dx, which becomes 2x minus 3x squared plus 3. Now, these functions defined per hand. What we can do is first clear the terminal and do all that business. And what I do is this. First, I have a term called epsilon, which is used for calculating the error between. It's not used for calculating the error. It's a good estimate of the error that's there in a iterative procedure. So what we first do is let x of 1 be 12. That's our initial guess. Then I have an iteration going on. I say x of I is x of I minus 1 minus f of x by df dx x of I. So basically, that's the procedure for Newton-Raphson, the iterative formula. And what I do is I update epsilon to x of I minus x of I minus 1, the absolute value. So what this does is, you would have seen here in the example that as you, just a sec, I'll move on to Newton-Raphson. I'll open the graph. Right. So as the iterations go closer and closer to the root, the successive iteration, let's see here, it's somewhere around 2.512. If you increase an iteration, what it changes is to 2.511. So the change is not that much. It's when they relate the difference between two successive iterations becomes so low that you can be sure that you have arrived near the root. You cannot exactly arrive at the root, but you can arrive at the vicinity of it. So what I'm doing here is I'm applying Newton-Raphson formula in a loop, and I'm calculating the difference between the previous value of x and the current value of x for the loop. And whenever this value becomes less than 0.001, I stop the loop and I say, let's stop. This is the value of the loop that we want. And after that, I've added some code just to plot and see how stuff looks like. That's not something that's necessary, but it helps in visualization. So let's try to run and see how this works. So we have it here. So as you can see, the actual root lies here, somewhere around 2.5, and the vertical stripes are the guesses made by Newton's method after each iteration. So it starts off somewhere at 12, then reaches 8, and here, and here. And then you see a lot of clustered points here around 2.5. And when the difference between these 2 points becomes less than 0.01, we actually say this accuracy is good enough and let's stop. And that's how we arrive at this predicted value of the root, which seems to be something around 2.511. And you can also see that the actual root lies very close to it. So if you want more accuracy, what you can do is decrease the error tolerance. So in order to make it more accurate, so you can always not do this and just say, let Newton-Raphson run for some 1,000 iterations, and only then I'll be happy with it. So that is something you can do. So I leave it as an exercise for you guys to use MATLAB or Octave and implement the bisection method as well, considering that we are short of time. So sorry, I'll have to rush a bit. And now that we have looked at how you'd go on about, oh, all right, sorry. Before that, are there any doubts in this method that I had implemented? If there are any, then please go ahead. All great. Do you want to speak? I saw. All right, I'll assume there are no doubts. Fine. If you guys have any doubts, you can always reach out to me later. Fine. Now, there's one more pretty interesting application of Fourier transform, that is noise. So, what is the first thing that comes into your mind when you think of noise? Might be something like this. A lot of screaming and shouting. Let's say you are in some fish market or you are in a very crowded traffic area and there are lots of cars honking and you feel pretty nauseous. So that is a kind of noise because noise in the most general sense is something that is unwanted. But the kind of noise that we'll be dealing with today is something like this. Say you have an old TV in your home or you switch to the cable channels. Sometimes you'll be able to see such a very flickering pattern of various colors on your screen. Or say you tune into a radio channel, but the resonance is not there. You'd be hearing something that is known as white noise. So that is what we'll be dealing with today. So some examples of noise, as I mentioned before, static or white noise on radio. And let's say if some of you guys are electronics enthusiasts, then let's say you have built some ultrasonic sensor or something, you would always see that there are always some fluctuations in the readings, even though there's nothing actually in front of the sensor. So that is also a kind of noise that seeps into electrical signals. And one more kind of noise that you guys would have probably seen is there would be some sort of grains in the photograph that you take with your phone if you are in a dimly lit room. So that is due to the thermal agitation of the atoms in the sensor of your camera, and that also contributes to noise. So in essence, noise is any unwanted random disturbance to the actual signal that contains meaningful data, but has been corrupted by this disturbance. I hope that's clear. Now, right, so here are some examples of noise. You would see a stark difference in the two images. One of them seems much smoother than the other one, which seems grainy. So this is the kind of noise that I was referring to in photographs. And at the same time, if you were to actually take in, let's say, some voltmeter or something, and try to take the voltage readings of a circuit which has pretty bad components, then instead of seeing something that looks like a good sinusoid, say when you switch on a sinusoidal AC source, what you'd be getting is a lot of noise. So how do we rectify this? Well, to rectify that, I want you guys to think in the frequency domain. In the past two examples, that is the grainy photograph and in the electrical signal that I had shown you, what feature do you think is common when you try to represent these signals in the frequency domain? It can be anything. Come on, guys. I have frequencies. Interesting. Yes, it has to do with the frequencies, and you might be right. So, for reference, I'll clarify this thing as well. Whenever we refer to something as high frequency, what we mean is that the value of that thing increases a lot in a very finite duration. So something like this is what would be termed as a high frequency component. But something that undergoes changes very slowly, something like a big sinusoid wave, is something you'd call a low frequency. So looking at this representation of noise, say in some 4 adjacent pixels in a photograph, what do you think the frequency is? Is it high frequency or low frequency? chat mode, so you guys can put polls if you want to. All right. It seems B as well. So just to clarify, the blue signal is the one that's noisy, and the red one is the actual signal that you want to send. So in case you're confused about what the noise is and the actual data is, the blue signal is the noisy signal, and the red signal is the one actually containing data. All right. Unfortunately, it seems a lot of you have answered B. The actual answer is A. So the way you can think of this is, see here, this electrical signal, the actual data itself is a sinusoid with a pretty well-defined period. From the graph, you can see it oscillates every 10 seconds or so. But when you look at the blue signal, that is the one with noise, what you see is fluctuates up and down a lot. So the frequency of that signal is much more than the frequency of the actual noise that you want to, actual signal that you want to represent. The actual signal has a period of some 10 seconds, but the noise oscillates every 10 milliseconds or so, as you can see from the figure. And the noise as in the image example as well, you'd see that the actual data that you want to represent, that is the color of the surrounding pixels, does not change a lot unless you are at some places like the edge of the face. But everywhere else, the surrounding pixels have almost the same color. So it is only when that you, so take for example a look in the noisy image around her nose. In the clear image, what you'd be seeing is the skin tone is almost the same, but in the noisy one, you'd be seeing a lot of pink and green values as well. And that is what is undesirable, and it's the actual noise in the data. So I hope that it's clear to you that in most cases, the noise that you find is high frequency. And it's also true that there are different kinds of noise, and the kind of noise that you get depends on the physical source. There's a very good Wikipedia article explaining various kinds of noise, but the noise that I've shown here in these two examples are of high frequency. So I hope that's clear. Now that we have identified something crucial about this noise, that is, the noise is high frequency, what we can start thinking of is in the frequency domain. Now, if you represent the same signal in the frequency domain, what you'd be seeing is most of the data would have low frequency components, that is with low modulus values of omega, but the components of the sinusoids with higher omega values would probably be noise. They can also be meaningful data, but in most of the cases, what they end up being is noise. So a good algorithm that we can follow is represent the function in frequency domain, kill off the higher frequencies, that is set the amplitude to 0, and perform an inverse Fourier transform and get back the function in time domain. This is what is known as a low-pass filter and has applications in signal processing. So a pretty obvious drawback in this method is you will lose out on actual high-frequency data if they were present in the signal that you are trying to denoise. Now, let's see where such a method could actually find some application. Some of you would have taken a few chemistry courses or have probably performed laboratory experiments in the 11th and 12th grade, would have come across something that's known as spectroscopy. What you essentially try to do is try to find the elemental composition of some mixture by sending out light waves through them and figuring out which frequencies actually get resonated, and after a lot of physical process, you get some readings. And what you would often see in textbooks are diagrams like this. You see pretty well-defined peaks at some particular locations. But if you were to perform the same experiment in laboratory, what readings you'll actually get is something that looks like this. And now let's say you don't want to manually figure out the frequencies and you want to write a computer program to figure out where the peaks lie. Now, if you pass on this data directly to the program itself, the program wouldn't be able to determine whether, say, a peak at -4 is any different from the noise that's there at -6. Because both of them look like they are going from something that's initially of low value and then they spike up and take some higher values. So how do you actually get meaningful data? The answer is simple. You do the same low-pass filter procedure that I had shown before. Now let's try to implement the same in Octave. So I hope my screen is visible and the code is visible as well. So what I've done in this procedure is first I set the X limits. So basically from -10 to 10 as shown in this figure here. And then I'm also generating 1,000 points from -10 to 10. Now there's a quantity that is known as the sampling frequency, which is given by n divided by t, which essentially tells you how often do you actually pick out data from the actual signal. So why is this important? Well, if you were to have an actual analog computer, you would be able to represent a continuous spectrum of values. But since we are limited in the digital world, the precision to which we can store data is also limited. So both in terms of the actual data and the interval in which the data is collected is discrete. So this is something that plays an important role while calculating Fourier transforms numerically. I won't be explaining a lot about the procedure to calculate Fourier transform numerically. It is something that can be done using the function FFT, known as the fast Fourier transform in Octave. What it essentially performs is something known as a discrete time Fourier transform, which takes care of these limitations of the time and both the amplitude being discrete, and uses some techniques to compute what would essentially be the Fourier transform when we would have an actual continuous spectrum of data. So what this BTFT does is it takes the value of the function at these discrete points. And note one more limitation as well. You cannot represent the entire function from -infinity to infinity. That would literally take up infinite gigabytes of space. So what you actually do is represent it in some restricted domain. And what BTFT assumes is, it assumes the function is periodic from then on, and then it uses some numerical techniques to actually compute the Fourier transform. And a consequence of this discreteness is something known as the Nyquist sampling theorem. For those of you who are curious, you can search this up and read about it. I won't be going into that now. So now that that's set aside, what I'm doing is pretty standard Octave business. I first set up these parameters, the time duration, the number of sampling points, and after that, I generate a list of X values, after which I actually compute the data. So F actual is the actual signal that you see here in this slide. So what I've done is basically take a bunch of scaled and shifted Gaussians. For those who don't know what a Gaussian is, it is this function e to the power -x square, which looks something like this. So what I've done is I've basically shifted the function by some units on the graph and also scaled it by some factors, say 10, so that the peak increases in height. But at the same time, we can shrink the duration as well by scaling the X factor. So this is what I have essentially done. I've created 3 such Gaussians, and one being this, one being this, and one being this. And I have scaled them with the appropriate factors to get the spectroscopy data that I have shown here. Now, I use the way that I add noise to this data is at every sampled point, I add 0.5 times some random value between 0 and 1. So this function rand is something that can be used in Octave to generate random numbers, or more technically pseudo random numbers. And what I've done here is generate a 1 cross n plus 1 list of numbers containing random values, because the X list also contains the same number of values. I generate a same array, an array of the same size, but with random numbers in them, and then I add them to the actual signal to get the noisy signal. So, if you guys want to see how this all looks, it's given here in the plot. So, the first function, f actual, is the one that's shown here on the top. It looks something like this. And when I add an array containing random numbers to the function, it looks something like this. And now the end result that we want is an attempt to denoise this data and get something that's more meaningful, something like the third plot shown here. So how do we do this? First, we get a list of the corresponding frequency values for this data. This is something that can be figured out using the Nyquist sampling theorem. If any of you want to learn more about it, you can always reach out to me after the session. And then what we do is we use this function f of t, fast Fourier transform, to find the Fourier transform of the function f fact, and we get f omega. Now I perform a low pass filter. What do? I set a threshold. Here I have arbitrarily taken it to be 10 Hertz, and I write a for loop. And for all the frequencies that lie between 0 and 10 Hertz, I set them to be 0. I set the amplitude to be 0. Now, you'd also see that I'm doing this, instead of doing this from 0 to 10, I'm doing it for 10 frequencies from the middle of the representation. That's because when you compute the Fourier transform, what you'll be getting is a list of frequency values from minus f by 2 to f by 2. So the actual 0 frequency will be located in the middle of the list. What you can do is, from the middle of the list, go some 10, calculate the number of points to the right and to the left of the middle, which correspond to 10 Hertz, and you can set the value there to be 0. Now, I do this procedure in this for loop of essentially making all frequencies which are greater than, I think I mentioned less than 10 Hertz, greater than 10 Hertz, because we only want the low frequency data to remain, because the high frequency is what is noise. So we only allow data from 0 to 10 Hertz to remain, and all the data from 10 Hertz to the maximum limit that has been calculated here, we set that to be 0. Once we have done this operation, what we get is another representation in the frequency domain. So now let's say you guys want to see how this all looks. What we can do is, first, directly plot f omega. If I run this code, what you'll see is, all right, just a second. Fine. Since f of omega is complex as well, it wasn't able to plot properly. I will take only the absolute value of f of omega and plot that for now. So what you'll see is this. A lot of the meaningful data is centered around here with the low frequencies, and you get the components relating to noise in the high. Once
Hi guys. So Navin is experiencing a little bit of internet issues. He'll be joined soon. Give us a few.
Hello. Am I audible now?
Yeah, you are.
Okay. Thank you. Sorry for that, guys. I think I won't share my camera. I think that's taking quite a bit of my internet resources, and yeah, I'll only share my screen for now. Oh, there's see the name spectroscopy was just something I've written. It's just a weird way of spelling spectroscopy. So for some reason, when I was thinking of the word spectroscopy, all I could envision in my mind was evil German scientist working in his lab exclaiming about spectroscopy. So that's just a fun tidbit that I added there. It's actually the actual spelling is spectroscopy. All right. I'll share my screen now. Can someone? Can you guys see my screen?
Yeah, you can.
Yeah, it's visible.
All right. So till where was I audible or visible? Did I show you guys the plot of f of omega in the Fourier domain? Yes. Okay. So I'll show you what happens to the plot once you apply the filter. What you see is only the low frequency components remain, and all of the high frequency components have been set to 0. Now, after this procedure, what I'll do is calculate the inverse Fourier transform of this new frequency data, which is done using function IFFT, shorthand for inverse fast Fourier transform. And once I get the denoised data, I'm using these functions to just plot it. And what actually happens is you start off with the original data, you add some noise to it, and the denoised function looks something like this, which is way better than the actual function here. And since we are only restricting to 10 Hertz, you can also see some of the sinusoidal nature around these points. Now, if you guys are curious as to what will happen if we decrease the frequency of the low pass filter even more, what would happen essentially is we'd lose out on data. So when I set it to 1 Hertz, what the plot looks like is something like this, which has way less information than when we cut off data at 10 Hertz, and it looked like this. Now, if I cut off data at say some 30 Hertz, what will happen is the peaks will look a lot more better, but at the same time, some of the noise, which has its frequency around 30 Hertz, will start to creep in as well. And you can already see some noisy pattern being formed here. So that is something that you have to keep in mind while designing such filters. You want to find a sweet spot where you don't lose out on too much data, but at the same time, you can remove as much data as possible. So, and there are even more advanced ways to denoise data. What we have done here using the low-pass filter is represent the function in terms of complex sinusoids and remove some of the sinusoids. Now, a sinusoid might not be always appropriate for each function. There's a theory in mathematics known as wavelet theory, which lets you find the appropriate, I should say, basis function along which you would decompose your actual function. And using those wavelets, you will intelligently figure out which all wavelets to kill off and actually get back the original data. A lot of research is going on right now in order to find these appropriate wavelengths using machine learning techniques themselves. So if any of you guys are curious, you can always read more about that. So this is a very brief way of very brief and elementary way to denoise data, and you can always go ahead and look up through the internet for more resources, and you'd always see more and more elaborate filters which work pretty well. And now, with that, we are actually nearing the end of the session. And before we end the session, I'd like to have a recap of what all we have learned in MATLAB, right from session 1 to session 3, just to ensure that we are all on the same page. The first session, we began with numerical techniques for root finding, being Newton-Raphson and bisection. Now, you guys can also type in anything and everything that you guys remember about the session on the chat, so that it helps each of you recall a bit more. So after that, we looked at differential equations, the classifications, and a few analytical methods to solve them. Which we looked at in session 2, Euler's method to solve these same equations numerically. And we also looked at some predictive character improvements to those methods. Now, Euler's method can be used to solve ODEs, but to solve partial differential equations, PDEs, what we learned was the finite difference method. And after the finite difference method, this morning, after looking at some exponential solutions to differential equations, we started off with Fourier series. After looking at some interesting properties of Fourier series, what we looked at was the Fourier transform and some minute properties relating to Fourier transform. And we also had octave implementations of the same. And how did we implement that? We did that using a practical example of noise and data. And with that, that's all from me. And that is officially the end of MATLAB session 3. I'm here to clarify any doubts that you guys have. So chat modes, you guys can circulate the last attendance sheet, attendance 4 that is. And with that, we all will end MATLAB session 3 formally. I hope it has been a very good learning experience for you guys. And in case you guys wish for any more resources from our side, we'll be happy to provide that on the WhatsApp groups. So feel free to reach out to us. At the same time, due to time constraints, I wasn't able to cover a lot more interesting stuff. I've added that as in the slides for the curious here. So if you guys have time, always feel free to go ahead and try stuff out. I will be taking doubts for now on. All right. This club was founded 2 years ago. This is the, I'd say, third year of the club. And yes, some of this, such as multivariable calculus, is something that was taught to us in the first year. Fourier transforms are taught to some branches of engineering, not all. A lot of this is something that most of us just learn through curiosity, just going on YouTube or reading random math forums. And I guess that's something you guys can do as well if you're math info. If you guys have any doubts regarding today's session or any of these sessions, you guys can ask me. I'll be here to clarify. Yes, important reminder. Yeah.
Yeah, I guess you can allow them to unmute now. End of session, right?
Oh, right. Yes. I'll change the meeting settings. One second.
I did it.
Okay. Yeah. You guys can insert it in principle. I'm not sure about tunneling effects. I'm not an expert in quantum mechanics, but what I know for very well is a particle in a box or a particle in the hydrogen atom and things like that. When you try to find the wave function solutions to the systems, when you end up with the Fourier domain representation, the momentum domain representation and the Persson domain representation of the same function, what happens is the product of the variance of the two is greater than or equal to h by 2 pi. That's the Heisenberg's uncertainty principle, I think. Oh, right. So, officially, the session is over. If you guys want to leave, you can leave after filling the attendance forms. We'll be here for a while to clarify any doubts that you guys have.
Also, Brad announced at the beginning of the meeting. So we have our own in-house competition. So please go check that out. Also check out our Instagram and YouTube page. All of that is in the chat.
Yes, also, do check out our LinkedIn page as well, and give some visibility to our Mathematics Club website as well. Everything that has been taught in these sessions is located there as well, and you'd also see links to our handles there. Maths to learn for machine learning. You can two important things that you need to know is probability and linear algebra. You can probably first take a few courses in them and then probably Google that will help. Yeah, importance topic of math for ML. Yes, as stated before, probability and linear algebra. Those form the basics and the essence of machine learning. If you're joining IITM this year, then congratulations. And usually applications to join the forms are rolled out somewhere around August or September, I think. You should be able to apply for a club then. Any advice on mathematical topics I should learn in order to proceed with theoretical physics? See, one, it depends on the kind of physics that you're doing. Physics would see inputs from a lot of branches of mathematics. Say you are doing a course in mechanics, introductory calculus and some real analysis should be sufficient. But say you are dealing with something like electromagnetism and you want to analyze stuff better in frequency representations as well, then concepts like Fourier series and Fourier transform come in handy as well. So it is specific on the kind of physics that you're doing, but in general, you'd see possibly every branch of mathematics and theoretical physics. Yes, multivariable calculus is essential. It's not only useful, it's essential. All right. So those who had attendance issues, you guys, and missed out on a form or two, you guys can reach out to us, mention your name, phone number, and email ID. If you guys have joined 4 teams, then we will also be able to verify the duration for which you were in the meet. And say you were missing for some 5-10 minutes due to some internet connection or something, we can grant you attendance then as well.
Also, if you already have 8 out of 10 attendance forms, there's no need to contact us, since you won't get any prize if you have 10 out of 10.
Yes, you guys don't need 10 out of 10 attendance to qualify in this summer school. Having at least 8 is sufficient. And right, one more thing, please do give a shot at assignment 2 if you guys haven't already. We know it's a tough assignment, but do the best that you can. We will be lenient in grading so that we ensure that those of you who deserve certificates don't lose out on your certificates. All that we ask of you is to show that you have put some effort from your side, and if we notice that effort in your submission, then even if some of the answers are wrong and we get an idea that you have tried to learn, then also we will try to grade you as fairly as possible. Now, one more thing is, as usual, we'll be rolling out assignment 3 as well shortly. And considering that you guys are also doing assignment 2 right now, we have the current deadline for assignment 3 is 24th instead of 23rd. If you guys still prepare extensions after a lot of requests, we might be able to do that. But at the same time, it's not feasible to extend the deadline for the assignment. So please try to do the best that you can. Where to mention name, email, and number. I'm assuming this is with regards to attendance. So you guys can contact any of the coordinators in the WhatsApp group. You guys can DM us. Right. I think someone was asking for a good resource on numerical methods. There's a book called Numerical Methods by Stephen Chapper. That is something you can look at if you're interested in. Right. We have short past half an hour beyond the actual time limit, so I guess we can probably end now. I thank everyone for coming and attending MATLAB session 3 with all of us. It's a pleasure having you all throughout the summer school. I make one last request. Please do check out our Instagram, YouTube, LinkedIn handles, and do check out our website as well. So thank you. That's all from my side.